We'll get started. My name is Frank. I'm your host. This is Payman, co-host. This is machine learning data mining. We're going to talk about feature engineering today. And congratulations to all of you who are here for the lecture, even though the midterm's due today, and there's another homework that's not too far out. Yeah. Cool. Last time we did multi-class linear classifiers. This is an easy lecture today. It's going to be super chill, like thanks to the midterm. Like, we discussed multi-class linear classification. So using linear models for classification where there's more than one output class. So yi in this, right? And we said we can train one. We can train one versus all. We can basically learn k different one versus all classifiers using a +1 -1 binary classifier. And we can take the weights for all k of those classifiers, which predict 1 for class C and -1 for everything else, and stack them up into a big matrix W, where every row is one of the parameters for one of the linear classification models. And we said we can do one versus all classification by simply just taking the C which maximizes this score, where this is a function of the class, right? So for a particular data item xi, you multiply by all of the parameter vectors wc from 1 to k, and then take the one that maximizes that. And then we said, well, actually you can do better if you construct a loss function that tries to make the scores output from the various models kind of compatible with each other score-wise, right? Which is to say, you really want the maximum of all of the weight of all the parameter vectors. So basically this score, you want this score, which is the parameter vector times the input item. You want the maximum one, but you want the score of the true class label to be larger than all of the other inner products, right? So we said, okay, well, we can do a multi-class SVM thing with the sum or max rule or whatever. Here's the sum rule, where we sum over all the data items, and we do the sum rule, where we're saying that for every C that's not equal to the true class label, right? So that's this term right here. We want to overall minimize jointly the parameter vectors for all k classifiers, right? And we'd like to make this thing as small as possible, which means making the inner product with the true class label as large as possible. And we want to make this thing as small as possible, which means that simultaneously as small as possible, which means, you know, pushing the inner product with all the other vectors and that data item as low as possible, right? So you can sort of look at this and grok what's going on by just saying, like, we're trying to make this as small as possible and this is small as possible. And the way to do that is to make the true class, the true parameter vector, the one that maximizes this quantity, and everything else. We want to learn parameter vectors for all of the other classes that are small in that particular instance. Okay, cool. And then we put some regularization on and said, call it a day, right? We did not do multi-class logistic regression, but we can do this in sort of the backward, still not probabilistic way here by basically smoothing a degenerate max thing, just like we did for the binary logistic when we derived the binary logistic loss. So a degenerate constraint, meaning that if we plug in a 0 vector for the parameter vector, this is automatically satisfied. So it's uninteresting, but we're going to fix this with the log sum exp trick. So a degenerate constraint in the multi-class case can be written like this. We want the inner product between the weight vector or the parameter vector of the true class times the input to be greater than or equal to the max over all the rest of the classifier score outputs for all of the C's. Yeah. Makes sense. So of course the C is going to include the Y, but that's totally fine. Doesn't really matter because we want all the rest of them to be smaller. As long as that's true, we're going to get the classification right. We can rearrange this and put, this on the right-hand side with a negative sign. Great. So what do we want? We want the right-hand side to be as small as possible, right? We want it to be bounded above by 0, so we want to push everything down, just like before. And what we can do is we can actually look at this max over a bunch of different classifiers and just smooth it with the log sum x, just like we did before. Okay, so we replace this max with log sum x, right? It's no longer degenerate, right? So if you set all the parameter vectors to 0, this turns into log k. Okay, so you theoretically should be able to do that, do better than that. And this particular loss is going to show up a lot, and you should be very familiar with it and kind of just put it in the back of your head that this is here. This is called the soft max loss, and it's the loss for multi-class logistic regression. It's also a loss function that you'll use very frequently when doing deep neural networks and having a final layer which outputs class probabilities or something like that. So you do multi-class classification using a deep neural network. The final layer will often look something like this. Okay, so just keep this in the back of your mind, soft max loss. This is going to show up again when we talk about neural networks, okay? Cool, all right. Just like for the support vector machine, this loss is for a single example. So in order to derive a loss for the entire set of parameters, this is a matrix W here, right? We sum over all the instances. And just looking at it, you can see that you try to make WC transpose XI, just like I said, big for the correct label, right? That's why I is the correct label. So if you make this big, there's a negative sign, so that makes it really, really small, right? And this approximates the max over all of the classes. So you try to make that as small as possible for all of the labels, right? So you don't want any one of the labels to come up and be bigger than this. That would be bad. And of course, just like for the multi-class support vector machine, we're going to regularize. This has all the nice, does all the nice things that regularization does, right? And this is just the L2 regularizer of all of the elements of the matrix W. If you look at this term, that's pretty clearly convex. This term is pretty clearly convex. And if you spend a little bit of time, you can derive the fact that this term is also convex, right? So it's clear for the first and third term, not so much for the second term, but trust me, it's convex. And this term is differentiable with respect to the model parameters. So you can use gradient descent to train this, okay? So when we start doing stochastic gradient descent, you can think about, for instance, multi-class logistic regression as an example of one situation where we would do that. Also not obvious because it takes a little bit of algebra to work it out. If you set k equal to 2, in other words, the number of different classes equal to 2, then this is equivalent to binary logistic, to the binary logistic loss and binary logistic regression. And that's not super obvious, although I think we'll get to that sometime in the future as well, when we do the probabilistic thing. So a couple of little details worth putting out in front of you. In the multi-class linear classifiers, our weights are this W matrix, where each row is the k weights for each of the different linear models. And to predict on all the training examples, we compute WC transpose XI for all C and I, right? Or in matrix notation, right? We want to form this matrix of outputs, which is just all of the data items on the rows, right? So you've got n by k, n by d, excuse me, and then WC transpose or whatever, the W transpose is going to be d by k. And out of this, you're going to get an n by k matrix, which is the outputs. So basically, all I was saying is you can compute all of the outputs for all of the data simultaneously with just a matrix multiplication of x and W transpose, right? The predictions that you make are just the maximum column indices of this matrix product of x W transpose, which is, as I noted, n by k. Okay, just a little detail. When you do implementations later, it'll help. A little notational detail, which will help in reading homeworks and writing stuff for exams and that sort of thing, is that The Frobenius norm for matrix is denoted in the following way. It's the square root of the sum over the rows and columns of the individual elements squared. And you can think about this as being the L2 norm of a vector constructed by stacking either all the column vectors or putting all the row vectors all in a row and then taking a transform to get a column vector, whatever, it doesn't really matter. The point is that you can use this relationship to write the regularizer that we've been talking about for multi-class logistic regression and for multi-class support vector machines in the following way. So here's the sum over rows and columns with the entries squared. This is the norm of a column or row vector squared, and that's just the Frobenius norm squared. Okay, so we will use this notation a fair amount. Just have it in the back of your head. It's pretty straightforward. Questions? Shouldn't be super straightforward at this point, but it can never hurt to ask. We could ask the class to say whether or not they think payment shirt is pink. Okay, cool. So today's kind of an easy lecture about feature engineering to try to make it easy for all of us. It's tiring and tired time of that term. So let's point out a couple of really obvious things. It should be obvious from the midterm now that you've done a bunch of linear regression models, right? Where you've needed to do a bunch of feature engineering in order to get scores that are good, right? Certainly some model structuring that in order to get your get good answers. Some machine learning projects succeed and some fail. What makes a difference? Easily the most important factor is the features used. This is a quote from Pedro Domingos, pretty serious machine learning guy. And Andrew Ng, says, coming up with features is difficult, time consuming, requires expert knowledge. Applied machine learning is basically feature engineering, okay? And you should be getting a sense of this at this point, right? The key point is really that we can do all of the different model developments and all that sort of stuff. That's really important, and it's what we sitting in this kind of chair do. But the reality is that better features will often give rise to better performance than will picking a better model, right? Although again, features and models are kind of the same thing in some sense, but it means like choosing an SVM versus a logistic regression model versus a whatever. Kind of all in the wash with respect to, if you really think hard and design a good set of features. And in fact, actually, a lot of the rest of the course, part 4 of the course, which I think we're still in part 3, but when we go to part 4 and we do unsupervised learning, a lot of this is going to be about basically doing some early kind of feature extraction pre-training kind of step to try to actually do automated feature engineering. But feature engineering of any kind is important, right? Because of course, good features would ideally allow learning with fewer examples, right? So if you have really, really good features, very informative features, you probably don't need that much training data in order to actually fit the model because the model will be relatively simple, right? And even if you do have a lot of data, it might be difficult to overfit even when you have a lot of examples. Such features would ideally capture the most important aspects of the problem, trends, whatever, right? And the thing that I think we try to get across in this lecture is the idea that there are certain invariances or problem invariances, like a classifier, a digit classifier should be invariant to slight rotations and scales and so on and so forth, or an image classifier should not care about shifts in color or saturation or something like that. And if the features that you engineer for a particular problem encode or have the same kind of invariances that the classification problem has, then that's good and will help generalization performance, because the features that you engineer themselves will be invariant to the same invariances that the classification model or classification problem has. And of course, there's always a trade-off between simple and expressive features. If you have simple features, because the model is going to be simpler as a result, the risk of overfitting is low, the accuracy might be low. Complicated features, accuracy can be high, but overfitting, there's a risk of it. So like a lot of the course where we say there's no best model, it's also true that the best features are definitely going to be dependent on the model that you use, right? So you might have the same problem, but you use a different model and you need to do feature engineering that's conditional on the kind of model that you use. So for counting-based methods like naive Bayes and decision trees, you have to think about the coupon collecting problem. So in other words, you need to choose features that you can actually estimate counts for, but still separate relevant groups, right? For distance methods like the k nearest neighbors, you want features that that result in data items with different class labels being far apart. And for regression-based methods like linear regression, you want to do feature engineering that leaves your features or lends to the development of features that actually have a linear, like a correlation with the labels, or the labels are linearly dependent on the features, right? And we've talked about a number of these things, but it's worth reviewing them and then introducing a few more throughout the rest. So when we're working with counting-based methods, right, we often want to do some sort of feature engineering involving discretization, where we turn continuous quantities like an age, right, into discrete quantities by basically indicating whether they occur in some sort of a range where 20 and 25 are the ranges here, and this is the interesting bit of the range, right? If we count in age groups, this in particular in these counting-based methods, this can help us learn much more quickly than exact ages, right? So in other words, if we're trying to subdivide ages or whatnot into if these are continuous quantities and we try to build a random forest or something like this, like the counting problem or the estimation problem of the leaf probabilities is going to be very, very difficult. Sort of like you using k-means in the first homework of in the first problem in the exam. Right. So great. So we wouldn't want to do this counting kind of thing for distance-based method though. So because like obviously the distance between vectors in this feature space is not the same as the distance between the items, right? So like the distance between 19 and 25 is only 2 here, and obviously the distance between these two is much larger than that. So you would want to use, you wouldn't want to use this kind of feature transformation or feature engineering technique for counting-based methods to transform continuous to discrete. We talked about standardization. I talked too long on that one. I won't talk so long on this one because we talked about this. We have features with different length scales, right? There's some question about whether or not we should convert to a standard unit. Regularization does matter here. This doesn't matter at all for counting-based methods. It does matter for distance-based methods. K-nearest neighbors will focus on large values, right? Like this is going to make a big difference for k-nearest neighbors, whereas this will not, right? So often we try to standardize to standard units, like writing everything in grams or something like that. And we need to worry about correlated features, because if they're correlated, then you can end up with your distance functions actually accounting, basically doubling up or tripling up or however many copies of the data you have on the distance computation based on the fact that the variables are linearly correlated, or rather are correlated, not necessarily linearly. We've talked about nonlinear transformations for regression-based models, right? There was a question even here about what kinds of autoregressive models you use to do prediction. So here's an example of the kinds of thing that you would model using an autoregressive linear model, and you probably would use relatively, or should use relatively sophisticated feature transformations, right? And there are lots of domain-specific transformations, which we'll talk about, particularly when we talk about convolutions in the next lecture. If you have sound data, it's natural to look at things in the Fourier basis or use spectrograms, which is probably the more practical thing to do, wavelets for image data, and convolutions, which we'll talk about next lecture. So the best feature transformations are application dependent. That's kind of what I said at the very beginning. It's hard to give general advice, right? And if you're doing applied machine learning like you did in the exam in the second part, right? it's a really good idea to ask domain experts, right? To have some idea of the right discretization or standardization or transformation, so on and so forth. And if there's no such expert available, then cross-validation will help. Or if you have lots of data, the deep learning methods we talk about in part 5 of the course are really about basically learning features automatically while also simultaneously learning a classifier or something like that. The light stuff for the rest of the lecture is basically features for really text today and images tomorrow. Okay. Oh, okay. A couple of things to think about, particularly when we're solving before we get into the text features. How do we use categorical features in regression? So here's a categorical feature. We've got a city which can take 3 values. We already talked about this a little bit, but let's just remind you that the standard approach is to convert this into a 1 of k or 1 hot encoding. So, this is the vector representation for Vancouver, Burnaby, Vancouver, Surrey, so on and so forth, right? What if you get, in this particular situation, a new city in the test data which you haven't seen? Well, a common thing to do is just to say, well, we just set all of those to 0, and the new city just uses information that is common across all of the cities, right? So that's fine. It's out of sample, not any of them. So we just use the other features. What's the effect of binary features in linear regression? If you haven't thought about it, it should be pretty straightforward. But if you haven't thought about it, suppose we use like a bag of words representation. So here's our entire vocabulary. It's just 3 words: hello, Vicodin, and 340. Our model is going to put a weight on each one of those words: hello, Vicodin, and 340, right? And the features are just going to be 1 or 0, whether or not the word appears, right? So if an email in this particular case has only hello or 340, the prediction is, just the first weight plus the third weight, right? And basically having a binary feature J increases your output for that particular item by a fixed amount. And that should be really obvious, right? So you have it, you don't have it, you have it, you don't have it, you don't have it, you don't have it, you have it, right? So basically that's what's going on, right? The predictions from such a model, a linear model with binary features, is a bit like naive Bayes, where we combine the features independently, but we're learning all the weights together, which means that the model tends to work better. Okay, so let's do some example applications that'll be a little bit fun. So let's do language identification. So we don't have data that looks like this. Instead, we have data that looks like this. So we've got a couple of English sentences and then a couple of French sentences, right? So what feature engineering should we do, Payman, to these sentences to solve this classification problem?
Probably we can use like prefix and suffix, like for words.
For each word?
No, for the entire sentence. Like finding the prefixes.
Okay, so you want to use the prefixes, and then what?
I have to think about it.
Yeah, okay, we got to think about it a little bit. Okay. Feature percentage of, well, you have to know. Okay, great. I love this class, even with like how many people are here today. 36 people. It's like, thank you for this class is great with the comment channel. It's maybe a little bit too much humor, but like the good suggestions are there. So okay, so we've got people saying, okay, we're going to do word to vec, and then we're going to combine these. That's kind of like what we did for the Trump versus Biden tweets. We did word to vec, and then we smashed them together. You could just jam this whole thing through some sort of an RNN. Of course, you need to have word to vec in 2 different languages. We're saying percentage of verbs, feature number of words, so on and so forth. Well, we need to know what verbs are. Yeah, okay, so if we have Unicode, we can look for these kind of Unicode characters. That's true, but most people forget that when they're typing in on just a regular keyboard and like that aren't French. Okay. All right, so cool. We can think about it for a little while. Here's like what these vectors really are. Okay, and I just want to make sure this is really clear, right? So a universal representation, now we're going to say it's bad. Now we can argue about whether or not it's bad, but a universal representation without any question is just to treat this as a sequence of categorical features. So this thing is in Unicode, or let's say it's in ASCII, right? So this is in, 0 to 255. This one is in 0 to 255, right? So this whole thing is in like 20 to the 255, 256 to the 20, something like that. Okay, so it's just one long bit string, right? Totally fine, right? If you don't like the fact that sentences are different lengths, you can just pad everything up to some length. Let's say all sentences are 1024 characters long, and everything else is padded, right? Great, no problem, right? Yeah, okay, so we've got some comments on this, but it's not so bad, right? You can just stick this into k nearest neighbors, and if you got enough data, it's going to solve the problem, right? We've got universal consistency, it's no problem, right? Okay. But basically, it throws out everything that we know about languages and language, and some of the things that you have identified in the chat channel, right? In particular, if you really think about it, it has to learn that vous starting from any position indicates that it's French, right? So somehow it has to go into this entire vector space and be like, oh, if it starts here, if it starts here, if it starts here, if it starts here, so on and so forth, it's a French sentence. That's not a good representation, right? It doesn't use the fact that a sentence is made up of words and so on and so forth. You need a ton of examples, and you risk, yeah, okay, so bag of words, okay, yeah. So what we know for sure in this particular case is that if we have a French and English dictionary, there's going to be some overlap between the two, right? There's words that are shared between the two languages, including how they're spelled, right? But what we can do is we can throw away the word order, and just the very presence of French words versus English words, or the kinds of morphological features that you're talking about, that will sort the problem. And the word order here is not important for solving the problem. Just merely the presence of the word is there. So this English versus French sentence thing is invariant to word order. Doesn't matter what the word order is, right? So if you use bag of words, we did this before, right? So we just count up conference, that goes here, international, that goes here. This is some long vector of all the entries in whatever dictionary you use, French plus English, French union English, and there's the cats, right? So now you have some vector representation of each sentence, right? It loses a ton of information, but again, because the task, like solving the task of identifying whether it's a French or English sentence, if I scramble all the words in the original sentences, you're not going to have a hard time figuring out which word is which sentence is English or French, right? So why is this, and this is basically what I'm hinting at, why is a bag of words better than a string of characters here? Well, when we ultimately learn the classifier, we're going to need less data, right? Because the representation captures an invariance that's true of the task. If you scramble the original word order, you still can solve the task. You don't need it, so you shouldn't train using it. It's much better to just get rid of it, right? So most of the features give a strong indication of one language or another, and it doesn't matter where the French words occur, right? It's going to overfit less because it throws away irrelevant information, right? The exact sequence of words isn't particularly relevant here. Okay, let's do another application, right? Word sense disambiguation. This is a fun one, right? So consider the two sentences: the cat ran after the mouse and moved the mouse cursor to the file menu, right? Word sense disambiguation, here and after WSD, classifies the meaning of a word. It picks out the sub-meaning in a dictionary entry. Mammalian thing or computer accessory. It's really actually not that easy of a task. You can do okay with bag of words, but you'll have some problems, right? If you use bag of words for these examples, her mouse clicked on one cat video after another, we saw the mouse run out from drain the computer, the mouse is gray. These are going to be ambiguous unless you have more context. You don't know exactly which mouse you're referring to here because the bag of words representation isn't enough. So we need to have some word ordering and contextual information, but we don't need it all, right? So we've talked about bigrams a little bit. Let's be a little bit more concrete here. So a bigram is an ordered set of 2 words, like computer mouse or mouse ran or whatever, and a trigram is 3 words sets, right? And these give a little bit more context than just straight bag of words. They include neighboring words as well as the ordering of the words in those pairs and triples. Trigrams and up to basically 5 grams are very widely used for various language tasks, but trigrams in particular. General case is called an n-gram. I've done a bunch of work on n-gram modeling. Of course, if you're going to do counting or whatever you're going to do, the coupon collecting problem becomes larger with large n of n-gram, right? So here's another example, part of speech tagging. So what are the parts of speech of all of the words in the sentence? There's, verb, noun, adjectives, adverbs, so on and so forth. So the part of speech tagging problem is the problem of labeling all of words with their parts of speech. There are about 40 common syntactic part of speech tags, and you can achieve about 97% accuracy on standard clean data sets now. And you do this by applying a word level classifier to each word. So, you're going to look at this word and you're going to try to do some feature engineering to predict its part of speech. Of course, you're going to have labeled data, which gives you the parts of speech, but now you have to do feature engineering to figure out how to do this, right? So, Payman, what features of a word should we use for part of speech tagging?
Well, isn't it, you want to find the verb?
No, I don't want to find the verb. I want to label the part of speech for every word in a sentence. Suffixes is what I think William means here. Yeah, you could use a suffix, right? So the 1 suffix, the 2 suffix, the 3 suffix. Yeah, yeah, no, that's great. And I agree with Nico's comment, by the way.
Prefix as well?
Prefix as well, yeah. First, second, 2 prefix, 3 prefix, yeah. How about the words that come after, words that come before?
Mm-hmm.
These sorts of things, right? So you now know how to do multi-class logistic regression as of today, right? And if you use these 19 features, this is feature engineering that took place over a long time in the field of natural language processing. So categorical features whose domain is all words. These are lexical features. It's basically a bag of words type representation, but really just the word itself is 1, right? So there's a categorical feature. Is this a verb or not? You just literally, all the words in the dictionary, and it's just a 1-hot encoding over all the words in the dictionary, right? The previous word, same thing. The previous word, same thing. The next word, so on and so forth. Okay, so that's like a 5 grams. So you're going to have, a very, very large, high-dimensional 1-hot encoded space so far. Categorical features whose domain is combinations of letters, right? So this again is going to be very, very high dimensional because you're going to have all of the combinations of letters, right? The prefix, 1-hot of what the prefix was, 1-hot of what the prefix of length 2 was, 1-hot of what the prefix of length 3 was, so on and so forth. Same thing with suffixes. And then binary features that are like shape, that are called shape features, right? Does it contain a number, a capital, hyphen, so on and so forth, okay? Cool. So theoretically, if we're all on the same page, and I said, okay, go build me a part of speech tagger and use multi-class logistic regression with L2 or regularization or Frobenius norm regularization. And here are some good features to try. You could just go off and do this now, which is pretty cool, right? That means we've gotten somewhere. We've established some common language, and you sort of understand what's going on in terms of feature engineering and training a multi-class classifier, so on and so forth. It's all good. Cool. I really, really want to jam with Nico on this because I want to be like, where's Lululemon? Drives BMW. Okay, you know, I apologize to anyone whom I've offended, who wears Lululemon and drives a BMW. I don't drive a BMW now. I am unfortunately wearing Lululemon, but anyway. So okay, we'll do a little bit of easy stuff more like. So let's say we have ordinal features. How are we going to use those? What's some feature engineering we could do with ordinal features? So we've got, you know, very bad to very good in some order. And the natural thing to do would just to give them numerical values that range from 1 to, say, for instance, 5 on the same scale. It makes sense if you're using decision trees to do this kind of thing. It captures the ordering, which is the critical thing, right? But with linear models, you might want to do something a little bit more, because if you just convert them to numbers, it assumes that the ratings are equally spaced. So here is just a nice idea for you to look back on in the future if you're ever doing a regression or classification with ordinal features. One thing that you can do is do not a one-hot encoding, but an encoding that goes from bad to medium to good to very good, where you continually add 1, such that the difference between these two is related to the weight for very good, and it can be a different amount. Like the weight that you get for a very good rating can be versus a good rating can be different than the difference between a medium rating and a bad rating, something like that. Okay. Anywho, all right. Questions? Nah, too easy. Okay. We'll finish up very soon. You can all go take a nap or finish up your midterms, okay? Last little bit. We've been thinking about like all these interesting problems, right? So we talked about the important email problem, but what about if we want to do personalization? So obviously, what is an important email to payment is probably different than what's an important email to me, although 340 is going to be important to both of us. So we can use all kinds of features. Bag of words, trigrams, regular expressions, so on and so forth, structural stuff about email, so on and so forth. And what we agree about is that there's probably some globally important messages, like, you know, this is your mother, something terrible happened, please call me right away. But again, payments might be important messages, might be different than mine, it's similar to spam, right? So how do we do this? Well, here's an interesting feature engineering thing to think about, right? So let's say you have, you know, 340s in the email or not, right? Let's now do the following transformation. Let's say 340 in the email, and then the next column is conditional, right? First feature, did 340 appear in this email? Second feature, if 340 appeared in this email, who was it addressed to? Right, specifically like, you know, 340 and user 1, 340 and da-da-da-da, right? Okay. The first feature will increase or decrease the importance of 340 for every user. And the second categorical feature decreases the importance of 340 for specific users, right? And it lets us or Google or whatever learn more about specific users where we have lots of data, okay? So basically this is the setup where we have like one of k binary encodings, right? The first feature, this global feature, moves up the line for all users. The second feature moves the line up for 340 for user 1, right? The third moves the line up when the email is to user 2, so on and so forth. Okay, so now we're talking about an absolutely ginormous number of features, but that's totally cool. You can absolutely do this, and this is actually like one of the ways that Google does this. So you have global features used by all users, and then you have local features for user 1, local features for user 2. And of course, this is a very sparse matrix. Most of this is 0, so you only have to store the user ID and listed non-zero features. You have your labels, and now you can do personalized recommendations for important or not. And of course, now we're going to have to think about some other ways of fitting this model, because you're not going to want to do a matrix inversion or anything like this, because this D is going to be absolutely huge. So we're going to do stochastic gradient descent, and we'll be happy with that when we do it. But that's it. Okay, good. So we did a little bit today. Probably the most important thing we did today is to introduce the softmax loss, which is the multi-class version of the logistic loss. You're going to see that in neural networks, and it's the basis for multi-class logistic regression. Good thing to put on the final examination for a Kaggle competition or something like that. We discussed very quickly feature engineering, although we've done this again. I think this is kind of the setup for thinking about features for different kinds of machine learning models, right? Bag of words, we've talked about it. It's not a great representation in general, but it's good if the word order doesn't matter when solving a problem. We talked about some text features again, like trigrams, other kinds of features like lexical, stem, and shape features, which try to capture certain invariances in text data and allow you to solve problems like part of speech tagging, so on and so forth. And then we said, basically, you can build really interesting models by putting conditional features in for doing like local and global simultaneous recommendations for like spam or important email, something like that. Anyway, next time we're going to do convolutions. Basically, we're going to do feature engineering for image and sound data, and then we'll probably be very close to the end of part 3, and we'll move on to unsupervised linear models. Okay, cool. That's it. Take questions about midterm, life, you know, payment shirt color, that sort of thing, for the remainder of the course time. Thank you very much for your time and attention. Can we use data from the midterm to predict the next tweet of Trump/Biden? If you have the feature extractor that we use, absolutely, you could totally use it to predict who made the tweet. Although that's a pretty easy thing to do anyway. And a more serious note, again, again, we're looking at basically conditional models here, not generative models. So there is no mechanism for generating tweets, unfortunately, not yet. What about a time series with words like markup chain? I guess, sort of. So if you want to do a generative model for tweets, then indeed what you would do is some sort of recurrent neural net. You can do it with an HMM. That's one way that people used to do it a long time ago, hidden Markov model, or just an autoregressive model that in fact actually outputs characters. Effectively, that is what GPT-3 is. It's just a big autoregressive model where the outputs are words. Well, the fun thing is we don't, so I think the question is who is winning the midterm? I don't know that that's, that the fun thing is that we're all going to, we're all going to win. That's the truth. And the reason why we're all going to win is the people who are overfitting on part 1, it's going to be very clear all the things that we've talked about generalization and model selection and these sorts of things, because the people who are overfitting to part 1 are not going to do a good job on part 2. It's very unlikely that the ordering will remain consistent between part 1 and part 2. So Dominic, this is actually a very interesting point as well, even though you say it in jest. I wouldn't bet on my model, okay? So there are some of us who, for instance, I have worked in the sports gambling industry, right? Setting price lines against which I have bet and other people have bet, right? So what you really want to be able to do is make predictions that you would bet against, right? And that's actually the purest measure of your own confidence in your own work and the correctness of your work, actually. Right? So what models are people actually using, like the BCCDC or the CDC, so on and so forth? Those models are SIR, SEIR type models. Planning as, give me a second, I'll pop something in the. Yeah, there's some real models that people are actually using. Can I post my model to GitHub after the midterm is over? Yeah, I don't see why not. Yeah. Especially if it does well, I might, you know, I might wait for the test results. All right, thank you all for your time and attention. It's been lovely, as always. Payman, I know I gave you a hard time. I'll wear one of my my pink shirts again relatively soon. I'm a big fan of pink.
Yeah, you have one picture too.
All right.
All right, thank you.